What?
I said I was hoping you weren't speeding to get home on time. With
Oh no, I wasn't.
the way it
I
looks
just,
outside, that would have been dangerous.
yeah, I would have called you if I wasn't gonna make it.
That's fine. Um,
Yeah, it's
yeah.
not very nice at all.
No, this is actually the days where I really thank God that I am a online tutor also. In fact,
Yeah.
it was a day like this that made me develop the online. When I first started tutoring, I didn't do online, and I lived in Colorado Springs, and I had 2 or 3 sessions in Denver that day.
Gotcha.
And I went off. I got out on the highways, and it was snowing like today. And I was the lead car of a series of 3 cars that the 2 cars on my left got in a huge, massive pileup.
Oh,
And I managed to barely escape it with my life.
that's lucky.
Oh, it was the scariest thing I think I've ever been in on the highway. And I immediately got off the highway and went back to my house and canceled those sessions and started working on getting online available.
Funny.
So, all right. So 10.3. I've looked quite a bit at 10.3. I've done some of the exercises at the back. Is your review material different than that?
Um, no, I'm just gonna send you the exercises that he's having us work on. Sorry, I just got home, so I'm sending it to you.
That's fine. No, go ahead. Send those. It's interesting. You know, I have 2 calculus books, and the one that you're using talks about vector-valued functions, and the other one does not. The other one treats the same subject by calling it calculus of parametric equations. Whoops, I lost the sound for a moment. Can you hear me?
Yeah, I can hear you.
Yeah, I accidentally was pushing the speaker. Anyway, the other book calls it the calculus of parametric equations. It doesn't mention the word vector function, which I find interesting.
Yeah, it's strange.
I think it's the same thing that they're talking about. When they do their calculus of parametric equations, you know, they have the arc length and the surface area and all of that also. It's just they don't put the I and the J in there. They don't use this linear combination of expressing a vector function. They just call it a parametric equation. All right. I just got an email. That's probably yours. Just one page? Or
Yeah,
more?
we're supposed to do 1 through 20. And he said we could skip like 3, 6, 9. Just skip multiples of 3.
Okay. Well, this looks pretty, this is 10.3 from the back of your book, right?
Yeah.
Oh, oddly enough, it's different than oh no, hold on. No, it is different than mine. Interesting. Wow, significantly different than mine. Is your 10.3 titled vector valued functions?
Let me check.
Or,
No,
yeah,
it's
under
titled
the,
polar functions.
what's that?
Polar functions.
Your section 10.3 is polar functions?
Yep.
Is that right? Wow. My 10.5 is polar coordinate.
Oh, we only have 10.3. We don't have any more than that.
You go to 10.3 and that's the last subchapter of 10.
Yeah.
Wow. My book has 10.3, 10.4, 10.5, and 10.6. And
Wow.
and 10, 5, and 10 is polar coordinates and polar graphs. And, okay, well, let me take a look at this. Well, so far, this is not calculus. This is just converting polar to rectangular. Should we look at one?
Yes, please.
Is that polar or rectangular?
Polar.
So, what are my equations that I use to convert one to the other?
I don't know.
Okay, it's...
Oh, I do know. It's
Good.
the R equals cosine and then it's all
I think
the,
it's x equals r cosine of theta, right? And y equals r sine of theta. And I tell you what helps me memorize it. Sometimes I wonder, does the r go here and the x go here, or do I have it right? Well, we know that cosine of theta is x divided by r, right? When you're looking at the unit circle and you have this triangle, there's theta, there's x, and there's r. So if you remember your unit circle from trig, then that helps you remember these two functions here. And then the third one, actually there's four of them. R squared is what?
x squared plus y squared.
And finally, theta is what?
I don't know.
Inverse tan of y over x. Now, the way I've always learned this is that's if x is positive. It's equal to the inverse tan of y over x plus pi if x is negative. So there's all of the equations that we're going to use to convert these things. So x is equal to r cosine of theta. Let's plug it in. What's r?
So, do we know the radius?
That's actually the polar coordinate. That's the, remember in polar coordinates we're looking at this. Basically, kind of think of it as a bunch of concentric circles.
Okay.
And the r that we speak of, in other words, that would be an r of 1. Excuse me, I didn't draw that very accurately. That would be an r of 1. Gosh. That would be an r of 2. And that would be an r of 3. And they're all positive. In other words, that would be an r of 3 also. So r here is square root of 2.
Then what's
Incidentally, the angle of these lines is theta. In other words, that's theta right there. When you think polar coordinates, think the unit circle in trig. Because that was really your first introduction to polar coordinates. So for this one, r is square root of 2. Cosine of theta, what's the cosine of pi over 4? Because that's theta. In other words, that's r and that's theta.
But then what happens when you switch to do the rectangular?
Well, we'll address that when we get to it. Let's first of all finish this. In other words, go in the other direction. We have to figure out what the rectangular is, and then we'll go the other direction.
Square root of 2 over 2.
Okay, times square root of 2, which means 2 over 2.
2 over 2, which is 1.
So, excuse me, that means x is square root of 2. Y is what?
X should be 1. Because cosine of theta is square root of 2 over 2, so then you
Excuse me, you're absolutely right. I got mixed up on my algebra. And what is y?
Pi over 4 times sine of square root of 2.
Y is actually going to be the same thing as x because the cosine of pi over 4 is the same as sine of pi over 4.
Okay.
In other words, y is r sine of theta, which is square root of 2 times square root of 2 over 2, which is 1 again. So this coordinates point, let me draw it, because you can draw both polar and rectangular on the same set of coordinates. They're located the same place. In other words, if I think of this as polar coordinates, then my ray is going to be 45 degrees. I'm going to go out a distance of square root of 2. So that's where my point's going to be.
Okay.
You with me?
Yes.
Also, that happens to be 1, 1. That's going to be a 45, 45 triangle, 1, 1, square root of 2. So my x and y coordinates of 1, 1 makes very much sense given a positive root 2 for r and 45 degrees for theta.
Okay.
Okay? So, let's see. Should we do one more of those? I'll let you direct based on how much you're understanding what we're doing. Let's see, we're supposed to, these are all polar, and we're supposed to find rectangular from these.
Okay.
So, should we do another? I mean, we got 4 of them in question 1. Let's just do one more real quick.
Let's do B.
In fact, let's do B or D, did you say?
B.
B, yeah, that looks a little tricky because of the 0. Okay, so what is x?
1. Sorry, r cosine theta.
Which is cosine of 0. What is 1 times cosine of 0?
1.
Okay, so x is 1, and y is r times sine of theta, which is 0. So these xy coordinates are 1, 0. And again, that makes sense if we look at it. It's this point right here. Notice that that has an r of 1 and it has an angle of 0.
Let's do D.
Okay, D is no more difficult than any of the others. So x is what? You did say D as in 1D,
yeah.
David?
Yeah.
Okay.
So x is negative square root of 2.
Times square root of 2 over 2, which is now minus 1. And y is what?
Whoa, you did that really fast.
Well, it was the same problem as 1, only it was negative square root of 2 as opposed to square root of 2.
So y is going to be the same thing.
No. Hold it. Excuse me. Yeah. Sorry. Okay. And plotting that point, we can see that that has to be in the third quadrant. Now, notice what happens if we try to graph that polar without going through the rectangular. In other words, there's my pi over 4 angle. There's theta. Okay? But r is negative. And the way you do that is you go backwards. So when you have a negative r, it's like doing a positive r, only you go in the other direction. So this point, in other words, this polar coordinates points in the third quadrant. If we were not converting it to xy coordinates and we were just going to graph that, I would go up 45 degrees and then I would go opposite. I wouldn't go to the right like normal. That would be positive r. Negative r goes in the other direction.
So in C, since the first one is 0, does that just mean x is 0 and y is 0?
No, that meant the angle was 0. You said B?
No, C.
C, excuse me. Yeah, that means that r is 0, and yeah, it's 0, 0, exactly. No matter what the angle is, actually. If you get an r of 0, your point, your xy coordinates are going to be 0, 0, because notice x is r times and y is r times. So if I have an r of 0, my x and y are both 0.
Okay.
Okay, let's try one like 2b, maybe. I don't know. Do you not want to do the even ones?
We're supposed to skip multiples of 3.
Okay, we'll do that.
Yeah.
I was just the only reason that that's a little different is notice that that's just an angle. When you see inverse tan of a number, that's an angle. It's like when you take the trig function of an angle, you get a number. But when you take the inverse trig function of a number, you get an angle. So B looks a little strange, but it's really 5 and whatever that angle is. That angle's like 57 degrees. You know how I know that?
How?
Because that's a 3, 4, 5 right triangle. And nobody knows the angles of a 3, 4, 5 right triangle except me. It's 37 and 53, approximately. I'm being facetious, but nobody really does pay much attention to the angles of a 3, 4, 5 triangle, right? I mean, you've known 3, 4, 5 forever, but do you know what this angle is?
Nope.
It's 57 degrees, and that one's 33. No, sorry, 37 and 53. 37 and change, and actually 56 and more change. So, I recognize that as a 3, 4, 5 triangle because the inverse tangent was 4 over 3, which is opposite over adjacent, so it has to be a 3, 4, 5 triangle.
Huh.
And it's in the first quadrant, so that would be whatever the radian equivalent of pi over, or of 53 degrees is. Well, that's okay. Let's not spend time on it. Let's do the ones you need to do. So,
it's 53.153.
Oh, okay. So we're supposed to do 3 next or 4? We're skipping we're doing every third?
Yeah, but I'm, okay. 1, 2, 3, 4, 5, 6, 7, 8, 12, 1, 2, 3. Okay, I can. Yeah.
So which one should we do next?
We can start 4. Sorry, I'm working through the other ones on 2.
Oh, we were supposed to do 2?
Yeah.
I'm really confused. I thought, So we were supposed to do 1, 2. Let's do we need to do 2, or do you know how to do 2?
I know how to do 2.
Okay, let's go to 3 then. Are we supposed to do 3?
No.
We're supposed to do 4?
Yes.
Okay, let's do 4. So here, let me leave that. We have the x and y coordinate, which is minus root 3 minus 1. Now, we know we need r. R is pretty easy to get. So let's figure out r. R is pretty much like the Pythagorean theorem. In other words, we're solving for the hypotenuse with our sides being the 2 rectangular coordinates. So what is r?
-1.
Well,
oh, negative square root of 3, sorry.
Well, first of all, r squared, so r isn't going to be negative, at least not our first answer. Notice also that when we take rectangular coordinates and convert them to polar coordinates, there's lots of different answers. There's not just one answer. It's not a unique solution. So that's why they said give 2 sets of polar coordinates. Well, let's find one. Well, one of them, r is equal to the square root of x squared plus y squared. Well, this is x. That's y. So what's the square root of x squared plus y squared?
I'm sorry, I'm really lost.
Okay, see what I have circled here?
Yes.
R squared equals x squared plus y squared.
Okay.
Well, here's x, here's y. So what is r going to be? So let me...
R is going to be the negative square root of 3 squared plus the negative square, plus the square root of, plus -1 squared.
Okay, so r equals the square root of 3 plus 1, or 2. When you square negative square root of 3, you get 3. When you square -1, you get 1. Okay, so r is 2. You with me?
Yep.
Okay, now let's figure out what theta is from the very bottom 2 equations. So is x, which equation do we use?
Plus 5?
This one right here, because x is less than 0. Yeah, the plus pi one, for sure. So theta is going to be the inverse tan of y over x, 1 over root 3, plus pi. What is the inverse tan of 1 over root 3?
Do you want me to do that on my calculator?
Yeah, you can look at that triangle and tell me.
Oh, 2.
Well, remember inverse tan gives you an angle, not a number.
30.
It's 30 degrees, or it gives you a radian. We always want to do these in radians. So that's pi over 6, right? Inverse tan of 1 over root 3 is that angle, which is pi over 6. So I can replace this with pi over 6 plus pi, which is 7 pi over 6. So there is 1 set of polar coordinates. Now let's just check to make sure that we are in the right quadrant, and we'll figure out our other possible answers. Well, if I go 7 pi over 6, that's all the way around to there, correct?
Yes.
And if I go r of 2, it's right there. So I'm in the third quadrant, and I've got that triangle. That's actually a 30-degree angle there, and that's 2 there. So I can figure out that these coordinates have to be minus root 3, comma, minus 1. That would be the sides of that triangle. You with me?
Yes.
Okay. Now, what is another set of coordinates for that point? For this point right here. I'm sorry. Yeah, what's another set of polar coordinates?
I don't understand.
Well, okay, let's look at this. This is actually an excellent example. What if I gave you the polar coordinates minus 2 pi over 6? Well, I would start out by going up pi over 6, and then I would go backwards 2 units to get to that spot right there. So this set of polar coordinates defines the same xy coordinate as this set of polar coordinates.
Okay.
In the same way that if I added 2 more pi and had 13 pi over 6, it would be the same point. In other words, if I go around this unit circle a couple of times and arrive at this point, that's going to be a different set of polar coordinates, but the same xy coordinate. Okay, let's do another one in 4. Let's do B.
So r equals the square root of 9 plus 16.
Actually, a very interesting thing happens here sometimes. What if, and maybe this is it, the only time in math I can ever recall where it is correct to divide by 0. What is this?
Ooh.
Before we go on, let's just look at this unique application because it's so interesting. It's not incorrect to divide by 0 when you're taking the inverse tangent. What does that mean?
0 over 2?
No, definitely does not mean that. It means a vertical line whose slope is infinity or undefined. So theta here would be pi over 2. That's how you define. If you're defining theta as the inverse tan, well, the tangent function is undefined at pi over 2 and all multiples of pi of that. So it is correct to, this expression is perfectly fine. And in fact, this is the answer based on that expression.
Oh.
Interesting, huh? So now let's finish this problem here. What did you come up with for R?
R is 5.
We're doing 4B. And theta is what?
Theta is the inverse tan of 4 over 3. So theta equals...
No, it's 53.
Yeah.
Okay. So that's that same angle. In other words, it's that 3, 4, 5 triangle, so it's whatever the angle opposite the 4 is. And that's the big acute angle. So that's the 53-degree angle.
Okay.
Okay. So I don't know what that is in radians. Did your calculator say what it was in radians?
I'm not in radian mode. 1 second.
Let's get an answer in radians just so we'll have, if you're going to review this, you might as well have the answers, have me write them.
0.92.
0.92 radians.
927 about.
Okay. And again, that's first quadrant, and the x and y coordinates were first quadrant. So it's always a good idea to check and make sure you're in the right quadrant by the time you graph your polar coordinates. Okay, let's look at C. So here we have 0 and minus 2. Oh, here's the one I wanted. This was the one I just made up. Notice that theta is going to be minus 2 divided by 0.
Yeah.
So first of all, what's R?
R is 2.
Okay. What's theta?
Do we have to add x?
Do we have to add pi, you mean?
Yeah, sorry.
That's okay. What would you get if you took just the inverse tan of minus 2 over 0? What's that equal to? Your calculator actually should give you an answer for that if you put it in. Really, for sure? Try it.
Yeah.
Do inverse tan of minus 2 over 0. It won't give you undefined. It won't give you pi over 2 as an answer, huh?
No.
But that is the answer.
Huh.
Notice that if you take the tangent of pi over 2, you get undefined, or same as infinity. However, pi over 2, it's not clear here because of this expression whether we need to add pi or not, right? Do we need to add pi or not?
No.
Well, let's look at our XY graph. Where's that point? Right there.
So yes.
So yes, that is 3 pi over 2. So this is the one case where I guess that's x is less than or equal to 0. I don't know if it's always that way or not, but I think it is always that way. I hadn't realized it until just now, that when x is 0, you do add pi. Actually, no, that's not true. You have to look at each individual case, because if my coordinates were 0, 2, I would be on the pi over 2 line right there, right? And yet I would still be looking at the inverse tangent of 2 divided by 0. So you add pi if x is equal to 0, you add pi if y is negative. That's kind of strange, but that's what it is. In other words, always look at where you're at in the xy plane. Make sure that where you end up with has to be in that same plane. So there's one answer. That puts me at 0, minus 2, right?
Yeah.
What's another answer?
2, 5 pi over 2?
Okay, that's an easy one. What's a harder another answer? About minus 2 pi over 2. In other words, how do I get to that spot? I'm trying to get to that point right there. Well, if I go up to pi over 2, but then I go in the opposite direction, 2 units, I end up right there at my 0, minus 2 point.
So could you also go to negative pi over 2?
Yes. Yes, you could.
Okay.
You got it. For you to ask that question shows me you understand it. All right. So let's look at D.
Radius is 2.
R is 2. I'm not sure that that's called the radius. I don't think it is.
R, sorry.
Yeah, and in fact, I'm quite certain it's not called the radius. I'm not sure what it's called. Wow, I've never heard that called anything. R, other than R, in polar coordinates. Maybe it is called the radius, but I don't think so. The radius is very specific, the radius of a circle. Well, of course, this would kind of be the radius of a circle. Maybe this is called radius, and I've just never known it. What's theta going to be?
Inverse tan of 0 over 2.
Which is equal?
Zero.
Okay. Do I add pi or not?
No.
Oh, I didn't write these properly here. I didn't change them up here. This is 2 comma 0.
I don't think so.
You're right. In other words, where is this? This is on the x-axis, right?
Yeah.
In other words, it's that point right there. Well, that's 0. So the angle is 0. Look at that. So the polar coordinates are exactly the same as the xy coordinates for this particular set. And what's another way to define that point?
You could go 0 to no. You could
What's
go
the opposite? What if you go the opposite? What do you use a negative 2 for r? What would theta be?
Negative 2.
In other words, if I do these coordinates, that means I go around to pi. Now, perhaps what's confusing here is I keep getting to this point and then I say go negative. Well, you get to this point, but you start from the origin and go negative. So I end up there. So minus 2 comma pi is the same point as 2 comma 0.
Okay. Okay.
Hold on a second. I got to try something. I want to see if Wolfram alpha tells us what the inverse tan of division by 0 is. Arc tan of 2 divided by 0. Indeterminate. Amazing. Well, I guess you're just going to have to trust me that that's pi over 2. Ask your teacher if you don't believe it, but it comes into play on 4C. So we needed to be able to take the inverse tan of 2 divided by 0 for 4C. All right, what next?
5.
Graph the set of points whose polar coordinates satisfy the given equation. Okay, now we're not talking polar coordinates, we're talking about polar equations. R equals 3. Well, let's look at what that would be. R equals 3 means I'm going to go out 3, but it's going to be all angles. No matter what angle I get, R equals 3. In other words, if you don't have a theta, then it's a circle of radius 3.
So that's all I have to do?
Well, graph the set of points. Yeah, that's all you have to do is draw that circle. If it said convert the polar equation to rectangular equation, then it would be x squared plus y squared, which is r, equals 3 squared, which is 9, which is the equation of a circle in rectangular coordinates. Remember when we were talking about polar coordinates and I said that there's some functions that are much, much simpler in polar coordinates than they are in rectangular coordinates. And the equation of a circle is one of them. The equation of a circle is as simple as it gets in polar coordinates.
Okay.
Next one.
7. And since r squared equals 4, then wouldn't r equal 2?
Well, actually, r equals plus or minus 2. Now, the question is that still just a circle of radius 2?
I don't see why it wouldn't be.
Well, certainly r equals 2 is that circle of radius 2. R equals minus 2. That's that same circle. In other words, no matter what theta you pick, let's say you pick a theta of pi over 2, and if I go minus 2, I end up there. So for all thetas, I'm always putting points on the outside of this circle. No matter what theta you want to pick, I'm creating that same circle.
Okay.
Okay. 9?
8.
8. Okay, theta equals,
So now we're giving them an angle?
yes, now let's look at what we're doing.
So now we're drawing basically a vector.
A line.
But
It's not a vector because it doesn't have magnitude. It has direction only.
okay.
Notice that r is not defined, so theta is the only thing that's defined. And they actually, I didn't draw it right, it's a negative pi over 4. Negative pi over 4 is that line. And for all r. So this thing goes on forever.
Does it have Okay.
And the equation of that line would be y equals minus x, a slope of negative 1.
Gotcha.
Okay. Going through the origin. 9 or 10? I'm still lost as to
10.
which ones we're doing. 10? Okay.
We're just skipping multiples of 3.
Ah, now I get it. He just likes to make it interesting, huh?
Yeah.
So r squared plus 8 equals 6r. So think for a moment. Huh. Bet you that's the equation of a circle also. It's not at the origin. Why do I say that? Well, there's no theta, so it's for all theta. For another thing, if I factor this, I get r minus 4 times r minus 2 equals 0. So either r equals 4 or r equals 2. So could that be two different circles? I don't think so. I don't think that's the way to do that. Let's look at it a different way. Let's figure out if we can come up with the xy equation here. Should be relatively simple. R squared is x squared plus y squared equals, or plus 8, equals 6 times r. Well, r is y divided by sine theta, which is the same as y cosecant theta.
I don't follow.
Okay, so all I'm doing is using these equations there. And for r squared, I put in x squared plus y squared.
Okay.
6 for 6. Well, if I solve this for r,
But r equals the square root of x plus y.
hold on, let's solve this for x instead. In other words, let's use this equation to solve for r. So if I solve the x equation, I get r as x over cosine theta. Choose x instead of y. And that would make that secant theta. In other words, based on this equation there, r is equal to x divided by cosine of theta. That's the same as x times secant of theta. With me?
Yes.
So this is the hold on. We haven't converted it yet. We still got a theta in there. I guess in place of, let me write this. Now I have a complete equation in terms of x and y. And the question is, what is that an equation of? Do you have answers on these for 10?
I don't.
Of course, it's going to be a graph. Well, whatever that graph is would be our, in other words, by converting it to polar, by converting it to rectangular like I did, at least now, if I had to, I could make a graph of this, by making a table of points and connecting the dots, or putting it into my calculator. This might be kind of tough to solve for y. I'd have to square both sides. I'm going to have all kinds of, I'm going to have a quartic equation.
Okay.
But I would think, how would I graph that without solving for y? Again, I could probably put it into Wolfram alpha and it would draw that graph. But I'm not sure we need to go there. In other words, once we've converted it to rectangular, well, you can can figure out the locus of points that fits that rectangular equation there. So 11, right?
Yeah.
Use a graphing calculator to produce the polar curve. Do you know how to graph a polar curve? You have the TI-84, right?
Yeah.
Do you know how to do that?
No.
Let's see what happens on Wolfram alpha. R equals 1 plus cosine of theta. Hold on. That's what that is. It's called a cardioid. It's called a cardioid because it looks like a heart.
How on earth do I graph that?
Well, first of all, you have to put it in polar coordinates.
Okay, let me see if I can. Okay, polar.
Okay. And then just go to where you define your functions, the y,
Oh,
and it should now say r.
1 plus cosine.
And it'll put in theta on its own. If you hit the what used to give you x, it'll now say theta.
Got it.
And
Ooh,
graph it, and it says find the appropriate window. Well, theta goes from 0 to 2 pi, and r goes up to 2. See if you can make it look somewhat like mine looks. In other words, get that whole thing on your screen. You might have to zoom in or out, or I would suggest defining the axis, because then you'll get a feel for that.
Yeah, that's what I'm doing.
Okay. What does it ask for when you define the axis?
Theta min, theta max, theta step.
Okay, so theta min, put 0 to 2 pi, and the steps can be, I don't know, anything, I guess.
Okay. For x min, I'm going to put -5 and 5. And then y, same.
And y needs to go from actually -2 to 2. And that will show you the whole. It asks for an x and a y, even when you're in polar coordinates?
Yeah.
And a theta, huh?
Yeah.
Okay.
This is a weird graph.
Does it look like mine?
It does, kind of.
Okay. The polar coordinates produce all kinds of weird graphs. Rose petals, in other words, graphs that look like this. And each one if you put in a certain polar equation, it will graph like that. It's really a parametric equation, I think. That's why you've got x, y, and theta. Yeah, it is a parametric equation. In other words, you have to tell it what x is, what y is, and what's theta going to go to. That's exactly the same as parametric equations. You give an x in terms of t, you give a y in terms of t, and then you say what t is going to do. Or if theta is your third parameter, you say, in other words, this rose petal here is graphed with theta going once from 0 to 2 pi. If I went from 0 to 4 pi, it would trace it twice. It would give another go around. Okay. You also have polar functions of these types of curves, like that cardioid or rose petal. Another type rose petal has the rose up here, not on the axis, and it draws kind of like this. If you put in parametric equations like this and you watch them draw it, you will see it trace out this curve as theta goes from 0 to 2 pi. And different curves get traced out. In fact, if I said, what is the length of these lines? Let's say I wanted to make this shape with string, and I needed to know how long a piece of string I would need. Then I would want to find the arc length of this shape. And to find the arc length of parametric equations, you've got the square root of dy dx squared, dy dt squared plus dx dt squared. That is the formula integrating that from 0 to 2 pi will give you the arc length of your polar graph.
Huh.
And this polar graph is two parametric equations. One equation, x is a function of theta. The other equation, y is a function of theta, with r being some constant in both cases. So we're really talking parametric equations here when we're talking some of these equations. Let's see. We did that. Then sketch the complete curve and identify the type of curve by name. Oh, man. That is disappointing that you didn't do Chapter 10.3. I can't tell you how much time I spent trying to understand 10.3.
Oh, I'm sorry.
No, that's okay. You told me you only went through 10.3 last time I was at your house, and I didn't look at your book. I just assumed that you were not seeing 10.4 and 10.5. Let's see. That was a cardioid, 11.
Yeah.
We're skipping 12, right? Did I get my pattern down right?
You did.
So 13. R equals 2 cosine of 3 theta. Go ahead and put that in.
I did, and my calculator's taking a really, really, really long time to graph it.
Really?
It's because I changed the data
That
set.
is a rose curve. I am looking at my other calculus book right now, and they have an example of r equals 3 cosine of 3 theta, and guess what? That's no different than that one. 2 times cosine of 3 theta. The 3 theta gives you 3 petals. And that curve, incidentally, you need to change your theta increments. The way, if you have theta going from 0 to 2 pi, it's going to trace that curve out multiple times. That's why it's taking so long, probably. Interrupt it and go from minus pi over 6 to pi over 6. I'm sorry. It would trace the whole curve out from 0 to 2 pi. But it's worthwhile seeing what happens when you let theta go from minus pi over 6 to pi over 6. Just do that for a moment.
I'm sorry, do what?
Put in that polar equation, r equals 2 cosine of 3 theta, but
It's
for
long,
the...
it won't let me interrupt.
Oh, you can't even interrupt it, huh? Oh, well, let me draw it. Here's what I just realized I can explain what I'm trying to say by drawing it. Here's what happens when you let theta go from minus pi over 6 to plus pi over 6. It draws just that petal right there.
Yeah.
Okay? And if you let it go from 0 to pi over 2, it draws that petal and this petal. It stops. So if I let theta go from 0 to pi over 2, it would trace that one time. Now, to figure out why it traces just this part when you go from minus pi over 6 to plus pi over 6, well, imagine what that angle is doing. There's your pi over 6 angle, minus pi over 6. And there's your plus pi over 6 angle. So as theta goes from minus pi over 6 to plus pi over 6, you're doing that part right there. And then as it keeps going, so I'm guessing that probably is minus pi over 6 to 5 pi over, or to 11 pi over 6. It would trace out the entire rows one time. You would have to integrate over the interval of 2 pi.
Okay.
Wow. And in my book, we can find the area of this thing. Through calculus. In other words, the area in polar coordinates is 1/2 the integral from angle A to angle B of your function squared. You probably, that's going to be the same as your 10.3, I'll bet. Does your 10.3 cover area and arc length of polar coordinates?
Let me check. Yeah.
But you haven't gotten there yet? No, you just started? Okay.
Yeah, we just started.
Okay. Well, since this is your last subchapter, will we be working on this same chapter next Sunday?
Most likely.
Okay. Yeah, because we haven't even gotten to the calculus yet. So
Yeah.
every single thing we did today was pre-calc. It was the same. We didn't do anything you haven't done in pre-calc. Of course, that was a while ago for you. So,
Yeah.
but that's, so we still have the calculus applications for polar coordinates, and that's probably what we'll work on next week. So that's good to know. I'll know which chapter to review. Even though I don't have, yeah, I've got it in your book also. It's just 10.6 in your book, not 10.3 for me.
Okay.
Okay?
Sounds good.
Good to go. Friday at 3?
Yes, please.
I will talk
And I
to
think
you.
we're going to start reviewing for the calc.
Okay. As I said, I got this calc, this kid that was a junior taking calc BC just like you, and he couldn't quite handle it, so they put him back in calc AB, and now he's preparing for his AP test. Well, you know what the teacher gives him for review material? This is the craziest thing I've ever heard. I'm going to show you. She gives him, hold on, she gives him this. It is the free response questions for the last 7 years of AP tests.
Yeah, that's what our teacher does too.
You got to be kidding me. That's the worst review you could ever do. There's the 2009 free response question, the 2008, the 2008, the 2010. Why would you want to give somebody the 20 toughest questions that have been asked in the last 10 years as a way to review?
That's what our teacher does too.
Makes no sense at all. It would be like you getting a 400 on the SAT math, and so when you and I review, us reviewing only the high degree of difficulty problems. I would never do that. I would start out on the easy problems and make sure you could do those, and then the medium problems. I would never go straight to the hardest problems. Why in the world
would... That doesn't make sense.
Doesn't make any sense at all. And these are super tough problems. I mean, these were a bear. In fact, I had an hour online session with this kid, and we spent a half an hour on this problem alone.
Oh.
So I think it's far better to do practice tests. I've got 2 practice tests on the Calc AB, and I got 1 on the BC, and you've got a couple, so I think that's the way we should go. Not these free response. That doesn't promote anything.
Yeah, those are brutal.
I mean, unless you're just so good that the others don't challenge you. If you're so good that the others don't challenge you, well, then that's different.
Yeah, but that's not true.
Well, we'll find out. We haven't really done any of the... We had one session where we did like 5 questions from a sample test you had, which I believe was a AP Calc test. And we spent an hour on like 5 questions. But I've gone through the whole thing, and it wasn't that tough. It was not a collection of all free response questions. So I will talk to you on Friday.
Sounds good.
All right, Emily. Bye-bye.
Thank you.